Hello, everybody. So this is Honors Pre-Calc, and we're talking about Learning Target 3. We skipped over Learning Target 2, which is about piecewise functions. But I want to do transformations before that because graphing piecewise functions is going to be a lot easier if you're good at transformations. Transformations are, they're very, very important, guys. Here are, what, 4 times 4? It looks like 15 parent functions. And it would benefit you to be familiar with all 15. You're already familiar with at least half of them. We got just a flat line, a slope of 0, a linear equation, an absolute value equation, a quadratic, I'm sure you know. The greatest integer function might be new to you. And then you've got your trig graphs. So a lot of these look very familiar to you. The light blue ones are the most popular in the real world, I would say. Actually, I would like to include sine and cosine with that. But if you can successfully go through this class with being amazing at these 3 blue, that would be a good thing, because these are very, very popular functions. A line, which you hopefully mastered in Algebra 1, that was a huge topic, will also be huge next year in calculus. Quadratics and exponential. Okay. And transformation, I gave the etymology here. I think this is interesting. Just trans is to go beyond or cross over, but then it also means change, and then form the shape of something. So transformation, we're changing the shapes of these things. And there are rules, and I know you remember some of these. Some of these may have eluded you recently. So first of all, this is taken directly from your text, which you have access to on MyMathLab. Shifting it left and right and shifting it up and down. So here you have the parent function. This is a quadratic, y equals x squared in the dashed black line. The red one is to the right 3, which is indicated right here, x minus 3 squared. And the blue is down 8, so x squared minus 8. And the difference, it's all about these parentheses. If you're within the grouping symbol, your movement is left and right. It affects the x value if you're within the grouping symbol. If you're away from the grouping symbol, it affects the range values, the ups and downs. That's a guideline. But then looking at this table will hopefully be beneficial for you. So the 2 black columns on the left are the several ordered pairs for just y equals x squared. This is the squaring function. If you plug in 2, you're going to get 4, because 2 squared is 4. If you plug in 3, you're going to get 9, because 3 squared is 9. The x squared minus 8, the purple parabola, is just the original parabola, x squared, minus 8. Well, what's subtracting 8 from what? From x squared, which is the result. So you take the result minus 8. In other words, you take the y value minus 8. Look at all these y values. 0, and if you subtract 8, you get minus 8. 4, if you subtract 8, you get negative 4. 9, if you subtract 8, you get 1. So the purple column, I feel students have an easier time grabbing onto, the movement up and down, because you're literally just taking the y value and you're subtracting 8, or you add 5, or whatever the translation is. Movement to the right 3 sometimes bothers people, but look at the table. Hopefully this will be convincing. In the original function, x to y equals x squared, 2 went to 4, because 2 squared is 4. But in this pink column, you need an input of 5 to go all the way to 4. Again, with 1 squared results in 1, but for the pink column, you need 4 to result in 1. I know there's other values that equal 1, but this 1 x value that results in 1 gets translated to the x value of 4, which results in 1. So minusing 3 as y equals x minus 3 squared really means you need to move all these x values to the right 3 to have the same results as it would have in the parent function, which is why it moves to the right 3 and not to the left 3. people see a negative and they want to go to the left, which is natural, but we have to correct that. It's the opposite of what you might think, to the right 3. And if it were x plus 2 squared, you would move to the left 2. Here's another example of moving up and down and left and right. We have another very, very common function, the exponential function. This one has a base of 2, and that's the dotted line here. 2 to the x. Well, here's the function notation, f of x plus 3. So f of x is y. Take all the y values that this will produce and then just simply add 3. That means everything goes up 3 spots. Here's the original y-intercept of 0, 1. Now it's 0, 4, 3 spots up. Here's the ordered pair in the original, 1, 2. Now it's 1, 5, 3 up. The green is f of x plus 3. So inside the grouping symbol, you move left and right. So this is to the left 3. And notice where it goes on the function. I'm replacing the input x with this new input, x plus 3. And it shifts it to the left 3. So what was originally 0, 1 is now negative 3, 1. You need to move your x3 to the left to get the same result in the y value. And what will help you understand this, I hope, is to remember that any real number raised to the 0 is 1. Moving on, more transformations. We have reflections over the x-axis, over the y-axis, over the origin. We'll just focus on the x and the y-axis here. But this one, this is the absolute value function, the parent function, y equals the absolute value of x. And now, if you could predict, if you could tell me what this one is without me revealing it to you, that's very good. You're in a great spot. Notice it went to the left 2. So inside the grouping symbol, I'm going to have x plus 2. But it also flipped upside down, which means it's a reflection over the x-axis. Oh, I'm sorry, left 4. I forgot my units. This is negative 10, so this is 2, 4, 6, 8, 10. So to the left 4. So x plus 4 will be inside the grouping symbol here. And a reflection over the x-axis means you need a negative outside the grouping symbol. Because outside of the grouping symbol, think of it as affecting the y. And if you want to reflect over the x-axis, all you're doing is changing the y values. When the y value was originally 10, it needs to be now negative 10, 4 to the left, and then now it's negative 10. What happened here? Well, this is a dashed line. This is the exponential function. And it definitely went up. So my original y-intercept was 0, 1, and now it's 0, 6. So it looks like it went up 5. But notice it's also changing direction. It's not flipping over up and down. It was flipping over left and right. And x is in charge of left and right. So the x values must be affected. So notice negative, you have the negative, the opposite of x here. Making the x the opposite will reflect it over the y-axis. It'll switch the direction going left and right. And we will practice these and they'll come more quickly. Some of these transformations are definitely more challenging than others. Here's one you've probably never seen before, an absolute value transformation. So let's think about a function. Here's a simple one. It's a quadratic because I know it's being squared. And there are 2 transformations. This x minus 4 and the grouping symbol means I went to the right 4. And this minus 3 outside of the grouping symbol means I went down 3. So I've got a quadratic. Imagine a quadratic centered at the origin, shifted to the right 4, and shifted down 3. So now the new vertex is 4, negative 3. Imagine that in your head, and I hope you were picturing the orange parabola. The black dashed, of course, is the parent function. Move this to the right 4 and down 3, and you've got this function. Well, that's great, but we want you to sketch the absolute value of this function. Much easier than you may be thinking. The absolute value returns the distance from 0. It'll always give you a positive number or 0 because distance cannot be negative. Well, look at this orange parabola has many, many different y values. There's a y value of 0, a y value of 1, a y value of 2, a y value of 3, etc. It even has y values of -3, -2. The absolute value will take all those y values and determine how far are they from 0, and then plot that. That's what absolute value does. It shows you the distance from 0. Well, the good news is all these positive y values will not change at all. Oh, excuse me, I was sneezing. Excuse me. All these positive y values will not change at all because this y value of +6 is, guess what, 6 away from 0. But this y value, -2, how far is this from 0? -2 is 2 away from 0. So this ordered pair down here is going to be reflected up right there. And this y value is -3. Well, how far is -3 from 0? It's 3. So this ordered pair is going to be reflected right here at 3 because it is -3 is 3 away from the 0. So picture in your head what this orange parabola will look like after you take the absolute value of all the y values. If you got something like that, congratulations, that's fantastic. Notice the left and the right arms, they just stay the same. That's part of the original parabola because they're positives, and if you take the absolute value of a positive, guess what? You get the same thing. But the bottom part of that parabola just got reflected up because the bottom part of that parabola was originally negative, and when you take the square root of a negative, the absolute value of a negative, you get the positive version of that. Notice the domain has not changed. The domain is still all real. The range has changed. The range goes from 0 to infinity. Last one. 2 more slides. This is the last idea though. Shifting horizontally and shifting vertically. I think the horizontal shift might be the most challenging one to think about. So let's start there. You've got a cubic function. The dashed black line is cubic. So 1 would produce 1 because 1 cubed is 1. 2 would produce 8 because 2 cubed is 8. 3 would give you 27 because 3 cubed is 27. Well, what if you put a 2 in there? A 2 is inside the grouping symbol, so that means it's changing the x value. And that's the red. The 2 would be acting as a 1/2 right here because notice it's in the denominator. So you take all the x values and you divide them by 2. So it's a horizontal shrink. Here are 4 ordered pairs that are on the original black parent function. You got the origin. 1 goes to 1 because 1 cubed is 1. 2 cubed is 8, so that's an ordered pair. And I also put -3, -27, because -3 cubed is -27. How do all 4 of those ordered pairs transform when you put a 2 in there? Well, it takes all the x values and it divides them by 2. So 0 divided by 2 remains 0. That's why the red also goes through the origin. 1, 1 becomes a 1/2, 1. So you only need to go over a 1/2 and go up 1. 2, 8 becomes 1, 8, so you don't have to go that far to get up to 8. Originally, we had to go 2 over to get to 8. Now I just need to go 1 over to get to 8. And -3, -27, you don't need to go all the way over to -3. You just need to go over to -1.5, and you'll still get -27. So all the x values got divided by 2. If this 2 were a 3, all the x values would be divided by 3. If this 2 were 1/5, 1 over 5, then all these x values would be multiplied by 5. And then our last one. Let's see if we can work backwards. The parent function is absolute value of x. You don't even need to know that. What you need to guess is what is underneath here based on these 3 clues. Notice the x values did not change. What is going on with the y values? Every single y value is being tripled. So you're you're multiplying every y value by 3. Now, you know what y is. Y is the absolute value of x. So I want to take 3 times y. So it's 3 times the absolute value of x, which is what this is. And graphically, it looks like this. The dashed line, of course, is the parent function. The blue line is the transformation. Every y value that was on the black has been tripled. For example, this ordered pair right here is 2, 2. I don't care about the x value, I just care about the y. The y value is 2, and if you triple that, you get 6. Here, the y value is 3. If you triple that, you get 9, right there. Here, the y value is 0, and if you triple 0, you remain at 0, which is why it again touches the origin. Here, the y value is 5, and if you triple 5, you get 15, and so it's off the charts, but it meets up with that blue graph right there.